Jorge, you're here to talk with us today about EDR Evasion Primer.
Yep.
What does EDR stand for?
To be honest, Endpoint Detection and Response, I think it is.
Sorry.
I just always say that.
Put you on the spot like that. I apologize. Sorry. Well, cool. What does Security Research Labs do? Are you based in Berlin?
Yeah.
You research
my
security?
team do red teaming mostly, but we do all kind of research, also in telco networks and stuff like that.
Sounds fun. Are you hiring?
Yeah, I think so.
Well, you know where to find Jorge if you have questions about the talk or about the company.
Yeah.
Round of applause. Please welcome Jorge.
Hello, everyone. It's really nice to be here talking about one of the things that I love the most for the past year, which is EDR Evasion. The idea of this talk is to give an overall idea of how an EDR works and a set of techniques that you could use to bypass any EDR. Like not individual flaws of any of them, but a set of techniques that you can use and a set of flaws that are present in any EDR out there. And in the end, we'll see how we can compensate these small gaps that we can find in any EDR in the market, basically. So first, a bit of me. I'm Jorge. I'm a red teamer at SRLabs. And yeah, I focus mainly on Windows security, Active Directory, and red teaming. And also for the past few months, mostly about endpoint security, preparing our payloads for engagements. So a bit of background. We obviously do red teaming. So in every engagement we do from a few months ago, I would say about a year ago, we always find an EDR. So evading an EDR has become one of our main objectives because we usually face them every time we try to get initial access. Because of that, we have a small test lab with a few EDRs, each of them running in an individual virtual machine and independent from each other. All of the features of the EDRs are enabled. The only feature that is missing is obviously cloud sample submission, because we don't want the hash to be shared and we don't want our samples to be submitted. But every other feature, including cloud analysis, with all the EOCs that the EDR has, everything that is included. We have 3 EDRs, Defender for Endpoint, which is basically the enhanced Microsoft Defender, Symantec EDR, which is an EDR from the Symantec vendor, and Sentinel-1, which is basically the EDR from Sentinel-1, one of the first EDRs that were available. And also an antivirus reference, but we are not going to mention which one. The results of this test lab were obtained in August 2022, but they are still pretty relevant because they are mostly the same. So first, how EDRs work. We are going to divide the analysis in 3 kinds of analysis. The first 2 analyses are the ones you can find basically in any antivirus, and that would be a static and dynamic analysis. A static analysis would be just looking at the file content and see if there's any malicious pattern inside and make a decision based on that. And dynamic analysis would be basically just looking, executing the sample in a controlled environment we call sandbox, and decide if it's malicious or not based on that. EDR add a new capability, a new layer of capabilities, which is basically what we call behavioral analysis. And basically that means that the malware is going to be executed on the host computer, and it's going to get all the data that it can from it, like all the telemetry. And based on that, it's going to decide if our malware is malicious or not. And if that's the case, it's going to kill it and create an alert. But let's look at it a bit closer. So static analysis would be the kind of analysis we do when a user has downloaded a file. First, the EDR, what it's going to do is going to analyze the file content and look for malicious patterns. These patterns can be anything like strings, domain names, assembly snippets, IP addresses, file hashes, whatever. The things that are inside the file and that can be obtained statically. Based on this, it has to make a decision. Is this malicious or not? Sometimes it's not only that it finds one thing malicious, but a combination of several things, and it makes a decision. Obviously, a good example would be if your if your binary has a metapreter shellcode or cobalt strike shellcode, things that you know that are really bad and that are going to perform malicious actions, that will be flagged. What we can do to avoid this is obviously obfuscate or encrypt the sections of our binaries that we know are malicious and that we know that could be suspected and could be analyzed by an EDR. But in this case, we need to be really careful with the obfuscation or encryption techniques we use, because the encryption technique or the decryption technique can be flagged by itself. So we could be flagged not by the content of the file, but by the technique we are using to decrypt our malicious content. So that's good if we implement our own techniques when we are creating malware. In dynamic analysis, we take a different approach. So the file has bypass static analysis, it's not malicious. So what the EDR is going to do is going to execute the same sample in a control environment, in a sandbox. And in a sandbox, you can see more of these patterns. You can see, for example, if the malware is performing network connections to a normal IPs, if it's performing registry changes, for example, or even if it's accessing memory regions that it shouldn't. For example, if it's reading LSAS or accessing different processes. Then, with this information, it has to make a decision and see if the malware is malware or not. If it's obviously bad, it's going to remove it, and if not, it's going to keep it. What we can do to bypass this kind of analysis is to make our malware clever enough to understand if it's inside a sandbox. That could be done in a lot of different ways. Some of them would be, for example, check the number of core processors, because usually sandboxes are limited in resources, or check the RAM memory we have. We can also perform some sandbox evasion techniques focusing on several users. For example, we can get the domain name of the user we are targeting to make sure it's only executing on a certain domain or by a certain user. And if that's the case, and if it's not what we are looking for, then we escape from the execution before doing the malicious activity. If we recognize we're in a sandbox, we just escape, and we should bypass dynamic analysis. Also, it's worth mentioning that if we implement a lot of techniques of evading dynamic analysis, that could be flagged by itself. If we are checking the memory size, the processors, everything basically, the EDR is going to get a bit angry at us, and it's basically going to also delete the file. So be careful with how many techniques you implement to evade sandbox. And then we get into a tricky part, which is basically behavioral analysis, and it's the thing that the EDR is implementing. In this case, you can see the representation of a common process injection technique in which we allocate memory, we write our payload in that memory region, and we create a new thread to execute that payload. You see two things here, it's kernel 32 and NTDLL. Kernel 32 will be the abstraction of NTDLL, and NTDLL, the low-level library in which basically most of the libraries of Windows depend. This is the low-level library that interacts with the kernel, and the EDR wants to know what is happening in these low-level libraries. So what the EDR is going to do is that it's going to modify. So first it's going to load NTDLL, and then the EDR is going to load its own DLL, and it's going to modify NTDLL in memory, placing some hooks to redirect the execution, analyze our behavior. To make it simple, for example, in a call to virtual alloc, what it would do is first call virtual alloc. Virtual alloc would call ntallocate virtual memory, which is the low-level function. And ntallocate virtual memory would go first to the EDR, analyze what is inside, and then go to the kernel and execute the call. With this information, the EDR knows exactly what we are doing in real time and can make a proper decision about our binary and see if it's malware what we are actually executing. Now let's see some effective techniques to circumvent these protective measures, specifically about behavior analysis that we haven't mentioned. A bit of background: in this case, we are obviously applying base evasion to everything. So we are evading static analysis, encrypting our payloads, and evading dynamic analysis by implementing some sandbox evasion techniques. And we are going to explain three techniques. The first technique will be unhooking, which is basically removing the hooks. The second technique will be direct system calls, which means that we are calling the kernel instructions going through a different way. And the third technique will be indirect system calls, in which we are going to do the same, but with a different approach. So let's take a look at this. This will be virtual alloc, which we discussed, and we are injecting our payload. We have bypass, static analysis, and dynamic analysis, and we are trying to inject in a different process. So we allocate memory. But the EDR is going to catch our syscall instruction, or our syscall, and it's going to analyze what's inside. And as we are allocating a known payload that the EDR knows is malicious, it's going to kill our process. What we can do, and like the first approach like anyone would take, would be to just remove these hooks. They are living on user land, so they are living in an area with which the user can interact to and can remove them. So the idea would be to remove this overwritten NTDLL, the DLL that the EDR has overwritten, and overwrite it with our custom NTDLL, with a fresh copy from disk that has not been modified. How we obtain this copy really could be in a different way, but we know that NTDLL is only modified in a certain part of the execution. So at first, NTDLL has to be in the disk completely unmodified. So if we just read it directly from disk, we can get a fresh copy and modify our in-memory NTDLL, overwriting it with the original one without any hook. We can also get a different approach because reading NTDLL could be a bit suspicious, and we can start a process in a suspended state and copy NTDLL from there before the EDR has even placed its hooks. So you can really get creative. The objective is to get a fresh copy of NTDLL and overwrite your in-memory NTDLL to remove these hooks and make the EDR completely blind. But we came across a problem doing this, and is that accessing NTDLL, the first technique, is common flag because it has been used by a lot of threat actors. And also the API calls we are using to overwrite NTDLL are also hooked, which means that the EDR is looking at you while you are trying to keep him blind, which is not a good approach. A different approach to the same problem would be something we call direct system calls. In direct system calls, what we are going to do is to implement our own system calls inside our binary. That means that instead of going through NTDLL, we are going to be calling them directly from our malware. In this case, we need one parameter to create our syscall, and that will be the system service number. Basically, it identifies which syscall are we going to execute. In this case, for example, we have the system service number or NT-allocate virtual memory, and we have a problem. And the problem is that this system call, the system service number, varies from Windows version to Windows version. So if we don't know which system we are targeting, we are going to get a really hard time implementing all of the system service numbers available in every Windows version. They can also be obtained dynamically, and it has been conveniently automated in some tooling like SysWhisper2, who had made easy to weaponize this technique, and it's really easy to implement with that approach. Once we have our system service number, our syscall instruction implemented, you can see that we are calling we are calling the kernel function directly from our malware and not going through NTDLL. And in that case, the EDR sees nothing. But again, we face a different problem. And it's that having a syscall instruction in our malware is something also suspicious. And there's a few software non-malicious out there that is performing syscalls from inside, if you think about it. Also, only the loader we are creating here is completely is letting the EDR blind. But everything we do after that is still going to be analyzed because the hooks are still in place. The EDR still sees what we are doing. So this is not a perfect approach. In this case, to evade the first problem, having the syscall instruction directly in our malware, we can do something that we can call indirect system calls. In indirect system calls, what we are doing is that we are going to prepare again our assembly instruction in our malware, but instead of that, we are going to scrap NTDLL and find a valid syscall instruction. Any syscall instruction is valid, and we are going to jump there instead of calling it directly from our malware. That way, the syscall instruction is called directly from NTDLL, which is how it's supposed to be, and we don't rely on having a syscall instruction directly on our malware, which is really good because it bypassed most of the detections we saw before. Now, before going into the actual test lab results, let's see some Windows internal things to those of you who are not used to Windows. We are going to explain two types of binaries, .exe and .dll. .exe is the common binary you can think that you double-click and execute. It is designed to run independently, and it has its own memory space. Because of this, EDR vendors are looking closer to these kind of binaries. So it's harder to bypass. Then we have .dll, which is the Linux implementation of SR libraries, and they need a host process to be loaded. So they share the memory space with the process that is loading the DLL. That means that it's way harder for the EDR to detect what is happening because the malicious actions are coming from a non-malicious process. Sorry. Yep. Now let's see a bit of the results we have. In this case, there's lot to explain, so I'm going to be a bit by bit. We test all three techniques against three different EDRs, the three different EDRs we introduced in the beginning, and we use two different payloads, Cobalt Strike and Sliver. Cobalt Strike is basically the benchmark for EDR vendors to test how well it's performing, and is a command and control that has been used and has been abused by threat actors for many years. Sliver, by the other hand, is an open source framework, also a command and control, and is gaining popularity recently, but it's still not as much as Cobalt Strike. The first thing we can see is that if we build our payload inside a DLL and it is loaded by another process, it really helps. As you can see, two techniques, direct syscalls and indirect syscalls, were both detected when we were building a .exe, but were completely undetected when we were hiding inside a DLL. Another thing we can see is that the detection we found is partly based on Cobalt Strike. So the EDR has some signatures that is targeting Cobalt Strike because it's the benchmark of the industry. And when you are using a different payload that is not Cobalt Strike, you are having a way easier time you have a really easier time injecting your payloads. Also, we can see that there's two techniques that work in every EDR and antivirus we tested, and they are direct syscall and direct syscalls. We discussed that sometimes the EDR could flag statically the word syscall, but as you can see, in all the EDRs we tested, this wasn't the case. Now, before continuing, let's see how an actual injection looks like, because we have talked about how we land our payload, how we land Cobalt Strike or Sliver in a host with an EDR running. But after that, we want to do more stuff. We just test the injection, but we didn't test what we can do after that. So for example, the first thing would be a user opening a shortcut file or a macro and getting injected our payload. So the malware is executed. And then what we are going to test now is all the actions that we can perform once we are inside the host, once we gain control of that host. And as you can see, the dynamic analysis of an EDR is not really good. The red is the things that are completely undetected. So in this section, we can see some actions we perform. For example, some really common actions we need to perform to conduct a successful red team engagement. The first thing you see is opening a SOX tunnel to pivot through the network and to tunnel over connections to that internal network. And that was completely undetected in every EDR. And this is one of the key features we need when we are using a command and control. Other thing would be data exfiltration, so downloading files from the host computer. And one thing that both EDRs include is keylogging, and it was only detected on one EDR and only on Cobalt Strike. So we can infer that it was only Cobalt Strike that was detected and not the keylogging activity itself. It was only a signature in Cobalt Strike. We can also add new capabilities. For that, we have, for example, execute assembly, who allow us to run CSR binaries directly in memory without touching disk. This is a feature that has been used a lot and that is still used, but uses something called fork and run. That means that we spawn a new process and inject our content in that process. Because of that, it's a common activity that has been abused for the last 2 years and is detected. It's detected in every EDR in Cobalt Strike and only in one EDR in Sliver. But still, it's something you should avoid. Conduct actions based on fork and run. We can also, to avoid this, run, for example, beacon object files that are pieces of code that can be run directly from the command and control and directly in the same process. If we run everything in the same process with the protections we have previously specified, we can, for example, run nanodump to dump LSAS or sharphound to enumerate Active Directory, and that was completely undetected. And another approach to the same problem would be inline execute assembly, which indeed perform the same action that execute assembly is doing, but instead of spawning a new process and doing fork and run, injects in the same process. And in that case, it's completely undetected. So we can infer also that the activity was detected because of fork and run and not because execute assembly by itself. The takeaway from here is that EDRs are highly ineffective detecting dynamic actions, and the main area in which they can be effective and that they are effective is detecting the first injection when you are getting initial access. But before continuing, let's see a full kill chain, because I told you everything and you need to believe me, but let's see a real scenario in which we are injecting from nothing to a host computer in which there's an EDR running. Because of this, I'm going to explain 2 different bypasses that we need to implement in order to create a realistic kill chain. They are not part of the talk, but they are really easy to understand. We want the user to download a shortcut, but we cannot download shortcuts from browsers, basically, because it's not allowed. So what we are going to do is just zip the file, zip our shortcut inside a file, and that would bypass the browser protection. The second thing we face mostly in every organization that is material off is a blocker, which prevents us from running certain applications. So what we are going to do is that point this shortcut that the user is downloading to an internal application that is present in every Windows available. So it's called lolbin, and because of this, we can execute this application because it's part of Windows and is signed and trusted by the system. One thing that MSHCA has, which is the lolbin we are using, is that allow us to download and execute remote payloads from our server. They are HTML applications that can be extended and can be, for example, use things as JavaScript, which allow us to execute arbitrary code. The second step we do, and our payload is going to do, is that the HTML application is going to download a DLL application and place it in the Teams folder. Once in the Teams folder, due to a DLL hijacking vulnerability, we are going to get persistence, and we are going to get a remote connection every time the user opens Microsoft Teams. Now let's see a demo, which is a video, because I didn't trust myself. You can see that first I receive an email, and I'm going to download the zip file, because I obviously trust my EDR. I'm spending a lot of money, so I'm going to be completely secure. I wait a bit. Almost there. I open the file, and you can see here that it says that it's a shortcut, but it looks like a PDF. And if you copy it to a desktop, it looks like an actual PDF. So it can be the user can be tricked into thinking that he's opening an actual PDF. Here you can see that profapi.dll is missing, which is the DLL we are going to download next. Now we open the PDF, and as it's downloaded from the internet, it shows this pop-up. But after a few seconds, it's going to open a real PDF. So it's going to mimic the real behavior of a PDF, and the user can be tricked into thinking that, okay, it worked. A PDF can do nothing wrong, of course. Now profapi is already there. So let's see what happens if we open Microsoft Teams. We got a session, and we now have control of that computer, and we can do basically whatever we want, whatever of the things we explained before in the dynamic analysis part. We can, for example, I don't know, list files. You can see that we are on the Teams folder as expected, because that's from where we're injecting. We can enumerate the processes to see if there's any malicious process, like any detection system we didn't anticipate. And we can do something that is not really used for red teamings, but it's quite scary, and it's taking screenshots. In this case, we are going to take 2 screenshots and move a bit the window to show you that I'm not cheating. Almost there. Yes. So there you have the 2 screenshots. So we have fully compromise a system that has an EDR running. And the key to this was basically detaching the execution from the download. As you saw, our first stage, our PDF document didn't do anything malicious. It's just open a random document and download the DLL into the Teams folder. But the Teams application was actually the one that was executing our payload. So the EDR really had a hard time correlating those two events. If we did completely if we did everything in one payload, it would be way easier for the EDR to detect those two actions and to correlate that there's a malicious activity. So as long as you want to build an initial key chain, you need to find ways of detaching these two steps to be successful in an initial access. Now let's see how we can compensate these protection gaps we find on the EDR. One question we can make is if we really need EDR on our endpoints, because I came here and I told you that I can bypass every EDR and they are useless in dynamic analysis, and you can think, okay, then why I should pay for an EDR? But the truth is that they are really useful. They make corporations way harder to compromise. If we know that an EDR is running, it's way harder for us to perform certain actions. We are going to invest much more time in testing every action we perform in our test lab, and we are going to be much more careful with whatever we do. And also, when we are performing a red teaming, there are certain actions that when there's an EDR, it's not worth doing. For example, if there's an EDR running, maybe it's not worth to dump LSAS and burn our whole operation to get an empty hash of a user we don't know the access it has. So really, an EDR slows an attacker a lot. It makes it way harder for an attacker to navigate through the network if there's an EDR. Every EDR can be evaded, but every EDR is going to make your life much harder because you need to double think everything you do. And also, if you are running a small company, an EDR is probably the best addition you can have, as they are not cheap, but they are probably cheaper than a set of good analysts, and they are going to give you a lot of information of things that are happening in your network about initial access, about they are going to prevent you probably against most of the automated things that you can see on the internet. They are really useful for that, but they are not perfect. If the industry is telling you that an EDR is going to detect everything that happens, that's bullshit. But they are really useful for what they intend to be. That is a nice tool you need to have to detect actions inside the network. Some external measures that we can have to improve our resilience would be heavy monitoring on common external compromise vectors. If you, for example, have a secure external perimeter and there's no 0-day, maybe you are good to go. But still, the attacker is going to try to get to your network through external compromise vectors, and you need to see why your user is downloading a shortcut. You need to obviously check why your user is downloading macro documents from the internet, or why your user is opening a ISO in a business laptop. Also, you need to secure your Active Directory and make sure that there's no attacker that lands on a workstation and can get to the main admin from there. So you need to follow the guidelines of Microsoft for tier 0 and for the tier structure, and make sure that that you review it every couple of weeks, not every couple of weeks, but every couple of time to make sure that it's working as intended. And also, you need to perform threat hunting on the data the EDR is giving you. The telemetry of the EDR is really useful. Like some of the things that the EDR is not showing you, for example, is that when I did the attack, actually in the EDR backend, there was some traces of what I was doing, but it's just that it wasn't that important for the EDR to show it to the user. But if you have a set of analysts that is performing and creating custom rules, they probably would see what I was doing, because there's a lot of telemetry that the EDR is capturing and that is worth for any company to analyze. So if you have an EDR, the best thing you can do is perform threat hunting and analyze the data the EDR is giving to you. And also, one thing that I don't see that much on the wild, but that is really useful if you have a company that can implement it, is running LSAS as protected process light, and basically prevent it from being dumped. It depends on the scenario. There used to be some bypasses that I think now are patched. But is it possible to prevent you from dumping ELSAs? And it will make the life of an attacker way harder, because that's a really common scenario of lateral movement. So running ELSAs as protected process light is a really easy thing you can do by running a GPO, for example. And if your company can run this kind of can run ELSAs in protected process light, then you should definitely do it, because it's going to get way harder for an attacker to move laterally. One thing one of our colleagues found in one of our engagements is that also EDRs are software that implement bugs, and this is really dangerous, because this software is deployed in basically every endpoint of a business. And that's, you can think, if you think about it, it's really crazy, because if someone compromises the backend of an EDR, he can do whatever he wants. So in this case, in one of our engagements, we gained access to the backend of an EDR through default credentials. And we also, one of our colleagues found 3 CVEs that were high severity. The CVEs are quite easy to understand, and basically the EDR has some endpoints that, and through an authenticated HTTP request, you can get the decoys, which basically are the things that the EDR is placing for you to check, and if you check it, then an alert is triggered, so you know exactly what not to touch. And you also can find the exclusion rules, which is something that is really powerful if you are performing a red teaming engagement, because you know exactly what the EDR is not analyzing. So as final takeaways, every EDR can be circumvented with enough time. That's a fact. And if you invest enough time, you are going to bypass any EDR that is going to face you. But the truth is that EDR really slow down hackers. And that's to be the objective and the takeaway we take from here. EDRs are useful, but we need to understand what are they useful for. They are useful because they are going to make our life much harder, not because they are going to prevent any attacker from getting into your network. Finally, you need to implement some complementary controls to make sure your EDR is not the only thing you rely on. So you need to build custom rules, you need to do threat hunting on the EDR, you need to do some hardening on your network. You cannot rely entirely in the EDR. But if you want to start increasing your security, I feel like it's a good point it's a good starting point. So that will be all. And it says questions, but I think there's no questions, so that's all.